All right, by now I think we all know the drill, so I'm going to get right to work, energy, and also power. So, question number one. Ooh, I should put my name here. There we go. EP. All right, so question number one. Motor is to lift a 50 kilogram box up to a platform that's 15 meters high. If the entire action takes 4 minutes, how much power is required by the motor? Okay, so clearly this motor is doing work. It's ultimately exerting a force over distance by lifting up that box. And of course, power is just a measure of how quickly or really at what rate that work is being done. So I'm just going to solve this problem by my usual methods. So motor, okay, so we have some kind of an object M, which is 50 kilograms. And it's being lifted up to a platform that is 15 meters high. Now, as you would have learned by now from my previous solutions, it doesn't really matter at what level this object is to start with. Like, I don't really know if it was on the ground or if it was already somewhere up high, or for that matter, it could have been at the bottom of a hole. The easiest way to do this kind of a problem is just to assume that or not even assume, but to declare that the lowest point reached is a height of 0. So I'm going to do that by just saying h is equal to 0. I'm going to follow that right up with an h prime equal to 15 meters, which is to say that wherever it started, my reference height of 0, it ends up at a height 15 meters above that reference. Okay, so if the entire action lasts or takes 4 minutes, so that's my duration of time, it's given as 4 minutes, and of course minutes are not our preferred unit for time, so I'll just do a quick conversion. I'll show my work nice and clearly here. So I know that every 1 minute is the equivalent of 60 seconds, so 4 minutes times 60, 120, that's 240, 240 seconds. Okay, so we got time in our preferred unit ready to go. The question ultimately is, what is the power rating of that motor in order to do so? So let's just visualize this. The box is, so let's just draw it over here, some object mass m, and ultimately there's two forces that are being exerted onto it. There's a downward force of gravity, as you would usually expect, and this motor, again, we're not really worried about how it's connected or anything like that. Through some means, the motor is connected to it, and I'm just going to call that a generic applied force. So it really is the power associated with that applied force that we're trying to figure out in this question. Okay, so in a situation like this, we just default to everything, assuming at the bare bones, the simplest situation that's consistent with the information we have. We're basically assuming that this thing is lifting nice and steady, nice and steady, nice and steady. We're definitely assuming that it's not accelerating throughout this lift. So since it is assumed really not to be accelerating, acceleration is equal to 0. And you know, again, like I've told you in the past, I have not solved these problems yet. I did glance at them before getting to work here, but I haven't solved these. I'm actually thinking right now, you know, just for the sake of completion here, I'm going to show two different solutions to this. I just decided this on the spot here. Okay, so at this moment in time, you literally could go down one of two different pathways. I would say that either one of them is fully correct. I don't think that either one of them is going to have a particular advantage. Like I'll often say that, you know, this is a quicker, more efficient way or something like that. I don't think I'm going to even be able to say that here. I think that these are both going to be similarly effective. So I'll show both just for the sake of completion, and you could, you know, pick your solution. You certainly wouldn't have to do it twice the way I'm about to. Okay, so how about if I spread this out? I'll just kind of say option 1. Okay, so option 1, and I'll distinguish that right away from what I will call option 2. Okay, so if it's going from a height of 0 to a height of 15 meters and it's going straight up, nothing really tricky here, I think I could say that it's going to travel a distance of 15 meters. And if it's traveling a distance of 15 meters in 240 seconds, I can tell you what speed it must have been moving at. The speed that it would move at would be the distance traveled divided by the time to do that. So that is my 15 over 240. So how fast is that thing moving? I'll tell you in a minute. 15 times 240 is 3,600. So speed is equal to, no, hang on, I definitely punched that in wrong. 15 divided by 240. There we go, 0.0625 meters per second. Okay, so I know exactly how fast that it's moving. And And I can also quickly calculate how big that force applied must be. Well, in order for it to not accelerate, these two would have to be the same size, right? I'll just do that as a little side calculation. I'll treat this as kind of generic to both solutions. The force of gravity is equal to mg, which is the 50 times 9.8. So that's going to be 490 newtons. So therefore the applied force must match that in order to prevent it from accelerating. It's just lifting up at a nice steady rate. So that will also be 490 newtons. Now, of course, if there's any doubt about that, like, wait a minute, how can it be lifting up if the 490 and the 490 are the same? A lot of people assume that means it could not be moving, for example. So again, this is little details that are nice to understand, but you don't really have to bring them into play every time. Technically, if this box was, let's just say, stationary on the ground, and then you hooked it up to the motor and got it lifting, technically this applied force would just briefly, and I want to emphasize it need not last for really any significant length of time. Briefly, it could have just been a little bit bigger than the 490 newtons, especially if we're not interested in making it go all that fast, right? That's actually a pretty slow speed. So if we just assume that applied force was briefly, I'm not going to make it mathematical here, I'm just thinking it through, technically a little bit bigger than the 490 newtons, but then it immediately settled into the balance of maintaining 490 newtons. Whatever little speed I got up to, it would then just maintain. I just found, I know that when I was a student, little things like that bothered me because I really didn't understand them yet. So I kind of knew how to get the right answer, but I didn't know why I was doing it. And that really bothered me for a long time until I kind of worked these little things out. Okay, in any case, the speed that it's going at is now known. The applied force, let me just go back to my green here for consistency. The force applied, which I worked out kind of separately, is now known to be 490 newtons. And I'll emphasize that it's even being pushed in the exact same direction that it's moving. This applied force is up, it's moving up, so there's 0 degree beta angle. One of our equations for power, which is what we're actually after here, right? Power is what we're looking for, is power of any particular force is equal to the size of that particular force multiplied by the speed of the motion times the cosine of the angle beta. And in my opinion, this is one of the underutilized equations. A lot of people, like if you look even at like physics textbooks and university courses and such, it often just gets overlooked for some reason. I think it's a fabulously useful equation. You can see how I'm using it quite nicely here. So the applied force is equal to 490 multiplied by speed of 0.0625. You know what? I'll just kind of slip in the cos of beta. This is just equal to 1. So I won't bother really continuing on with that in my written work. So I'll just grab my calculator, 490 multiplied by 0.0625, which is a power for that applied force, ultimately, in other words, the motor, of 30 decimal to 3 significant figures, just a 6 there. And of course, the unit of power is the watt, which is a shortcut for joule per second. In other words, this motor would be doing work at a rate of 30.6 joules per second, but we're definitely going to record that the way I've shown it, with watts. Okay, so I'm done this problem, but again, just because I'm trying to explain things, let's go back and try something a little bit different. Let's try option number 2. Okay, so avoiding what I've already done because I don't want to repeat it, how about if I think of the other equation for power? I already emphasized this equation for power, force times speed. How about if I just think of power is the work that was done divided by how much time that it took to do that? So let's go ahead and do that. We'll calculate the force. Well, actually, I won't recalculate. I'll take advantage of the fact that I already did that. Well, actually, technically it was this one, but the same value. And I'll figure out the work and then figure out the power from the work. Okay, so by the way, it was somebody pointed out to me that I say "okay" a lot when I'm teaching. I actually in my classroom when I'm physically there, and I actually listened back to my recordings of me solving these problems, and man, it's true. I say like "okay" an awful lot, and I am going to make zero effort to stop doing that. By the way, because that would just mess me up. So okay, let's get back to work here. All right, the work done is equal to, by the applied force in particular, is equal to the applied force, F applied, times the distance over which it was applied, multiplied by the cosine of that beta angle. So the work done by the applied force is the applied force, which, again, I previously worked out to be 490 newtons. I know that it's traveling a distance of 15 meters, and of course a cosine of 0 degrees. So how much work was ultimately done here? I'll calculate that separately. 490 multiplied by 15, and I'm getting an answer of 7,350. 7,350 joules of work was done. Okay, now, again, we were after the power, though. So let's remember that power is, for any particular force, the applied force, is the work that was done by that force divided by the time that it took to do that. I won't bother with a subscript on the time. Okay, so that means that the power done by the applied force is the work that was done, 7,350, over that timing, which was, again, 240 seconds. You can see more naturally how the units of power are joules per second, I hope, because this is, I don't write my units when I'm just doing the math, but this is a measure of joules, and this is a measure of seconds. So, yeah, power is joules per second, which we call a watt. Okay, there we go. Back to that. So, the power done by the applied force, and I have so much confidence, I don't need to calculate this on my calculator, but at the same time I feel somehow compelled in case I screwed something up, so double checking myself. 7,350 divided by 240, and whew, yes I do. I get the exact same answer, so 30.6 watts, as it should be. If I had gotten a different answer there, I'd immediately know that I screwed up one or both of these solutions. So it's kind of reassuring that they agree with each other. Physics ultimately should agree with physics, no matter how you do it. Okay, that's good enough for number 1. I'm going to press ahead. I'm not going to rush, but I'm going to just try to kind of march along through these things. Number 2. A car of mass given 750 kilograms, moving at that speed, coefficient of friction, and there's a little asterisk on here. Yeah, Mr. Dawson and I talked about this and wondering whether we should even bother to mention it or not, and ultimately we decided that sure, we'll just kind of slip this in here, because technically this is not friction as we learned it in the past. Usually when we think of friction, certainly the way we learned it in 30S physics, is we thought of like surfaces like sliding, like a block on your desk, or a tire of a car if the brakes have been slammed on and it's like screeching to a stop, or even like if it was braking more gently. This is actually subtly different, but I will tell you right now, it's not going to affect the way we're going to use the physics. Okay, so technically this coefficient here of friction is really called a rolling kind of resistance. So if you really wanted to be proper about it, and you would not need to for the sake of 30S physics, you can call that a coefficient of rolling friction. It's not really a static, nor is it a kinetic. And if you recall values, because we actually dealt with tires and roads a lot in the earlier part of the unit, and we generally used values that were at least in the ballpark of real world. Different tires, different surfaces will have different coefficients, but you may recall that the coefficient of like static friction for a tire on the road was often like 0.8 or even higher. So this is rolling resistance. When you have a tire that's just rolling along, even without the brakes being applied or anything like that, there is some resistance for that tire to roll. This is especially true if the tire is not like magically perfectly circular. And by the way, even a really good car tire is always a little bit flat at the bottom of the tire. that air in there is not strong enough to like rigidly keep that tire in a perfect circle, and so it is completely normal for the bottom of the tire, the part that's in contact with the ground, to be flattened out a little bit. And of course, as that tire rolls, that flat part continually changes, and it's ultimately that causes this rolling resistance. That's exactly why, for example, a train has steel tires, because a train, which is not really a vehicle meant to speed up in a hurry, nor is it meant to stop in a hurry. Really, it's just maintaining constant speeds by and large while it's in motion. They really want to minimize that rolling resistance. So a train with its steel wheels on a steel track really has a low coefficient of rolling resistance. But it's not really necessary for this problem. So I just, after saying that I was going to march along, I just wasted a bunch of time talking about it. But you could have fast forwarded it. It's your fault, not mine. So let's get to it. Mass equal to 750 kilograms. Moving along at a speed of 30 kilometers per hour. I'm just going to take my shortcut of dividing that by 3.6 on my calculator. So 30 divided by 3.6 to 5 significant figures. 8.3333 meters per second. I don't need the rest of those threes, and I don't need a repeating 3 either. This is plenty good. Okay, so there's that. This coefficient of rolling resistance, I'll just put it up here, 0.08. And again, the question is associated with power. So what is the power? Let's think of it as an applied force, because this car is, the engine and all of the parts, of course. Ultimately, there's something pushing this car forwards to counteract that rolling resistance. In fact, if we just make a quick little diagram here, if this represents the car, and the car is, let's say, moving to the right, there would have to be something to help that car push along forwards, and that would be, it would ultimately be another simultaneous interaction of the tires on the roads. Complicated physics to tell you the perfect truth here, but the long and the short of it is there's an applied force kind of maintaining that movement. You can think of that as the act of the engine through a complicated chain of connected parts. But nonetheless, it's there in order to counteract this rolling resistance of just the fact that the tires themselves are rolling. So think of it this way, if the car suddenly ran out of gas, or if you just slipped it into neutral or something like that happened, the car would gradually come to a stop. And one of the reasons why would be because of this rolling resistance. In the real world, there'd additionally be air resistance, but we're defaulting in our problem to assuming that's not at all present. There's be a normal force and a force of gravity. We know that would be mg. We know that in this case it's simple. There's nothing complicated about this. Vertically, it's not accelerating, so that would have to be the same size as the force of gravity. So let's just say it is also mg in size. Okay, so what is the power associated with the applied force is what we're looking for. Well, you know what? Since we have the speed here of 8.33, and I clearly have information to work with forces, I'm thinking of a solution that is going to be more akin to my option 1 of question number 1. I'm thinking that I'm going to be using something kind of like this. In fact, exactly that equation just applied to the new situation. So if I can figure out the applied force, and if I could figure out how fast it's going, well, I was given that. Beta is going to be 0 degrees. I think that I'm pretty well set to kind of work towards this version of the power equation as compared to the work divided by time version. Okay, just back that out. Okay, back where I was. Yeah. So let's kind of, in order to find this applied force, let's focus for a moment on the applied force. Well, if we are going at a constant velocity, then that means that there is similarly a balance in the x. This forward force from the applied force and this oppositely directed resistance force must be matched in size. Okay, so let's do it this way. The power by the applied force is equal to the force applied multiplied by the speed multiplied by the cos of beta as it pertains to the applied force. I'm just going to do a substitution, and remember I'm working with sizes here. There is no need for, at least in this power equation, there's no need for which way is positive. Power is scalar. Work is scalar. We don't need to get hung up on which way is positive. When we're doing vector equations, equations like Newton's second law, and our kinematics equations, direction really matters because those ultimately are vector equations. This is a scalar equation. That's why, in case you're wondering, like, why didn't I state which way is positive? That's a habit that I usually insist on, especially for the students in my section. You'll know that I'm kind of like really picky about that. I'm not forgetting to do it here. It's literally not needed here because this is a scalar equation. So the applied force, which is the same size as the resistance force, can be calculated as mu times the normal force, specifically that rolling resistance. So the applied force is equal to the rolling resistance in size, so a substitution of one for the other. And then the rest of this equation, speed, which I know, cos of 0 degrees, the applied force is forwards, the car is moving forward, so 0 degrees. And that means from this point forward I won't write that cosine in because cos of 0 is 1. So the power by the applied force is mu 0.08 multiplied by the normal force. We've already established that the normal force is equal to the force of gravity, m times g. So mass 750 times g 9.8. That right there, if you want to think of it, just kind of visually blocking it off, that is the normal force. Multiplied by the speed, which we were given as 8, well, I converted it into that unit, but 8.3333. And that should really do it for this question. Just grab a calculator here. 0.08 multiplied by 750 multiplied by 9.8 times 8 bunch of threes. So, to three significant figures, this is, because my calculator says 48999, etc. So to three sig figs, this would round off to 4,900, so 4,900. Technically, that's only two significant figures, but I'm actually forgiving on that one because I'm not losing anything. Like, even if I force this to be significant through scientific notation, it would legit be a 0. So I'm okay to just kind of write it as 4900. And of course, power measured in watts. There is that. Good enough. Okay, what else do we have here? In part B, okay, so repeat of the question, but this time we're going to be going up a 15-degree incline. Okay, so let me revisualize this. So there's an incline, and I'm not drawing it to scale because that is definitely visually larger than 15 degrees, but I often like to exaggerate these things anyway, just for the sake of visualizing. So alpha, the angle of the incline, is known to be 15 degrees. And there is this car which is driving towards the top of the incline. So it's very much like what we had a moment ago. There's an applied force. There is a force of resistance. But this time, the force of gravity, which is down, is not very convenient to work with, right? Its components are going to be easier to work with, just as we learned in the inclined plane part of the course. So let's kind of slip this in here. There's also a force of gravity component that is parallel to the surface, and there is additionally a force of gravity component that is perpendicular to the surface. You can use x's and y's if you want to, but again, because I'm thinking ahead a little bit to scalar equations, I'm less concerned about positives and negatives in the long run here. So yeah, the forces do have directions, like each of these forces is very much a vector, but again, kind of being aware of the nature of the problem, I'm leaning a little bit away from keeping track of positives and negatives as I normally would. So what else is there? Well, of course, there's this normal force, F normal. Now, ultimately, we're asked to find the exact same thing. We're asked to find the power from the applied force again. The major difference here is that the applied force is no longer equal to the rolling resistance. There is a helper here alongside the rolling resistance. So in order to move up the hill at a constant speed, which we are still doing, it's the only change is that we're now going up an incline, we're going to now require that the applied force be equal to those two together. So let me just kind of slip that in here. It's the rolling resistance added to the force of gravity parallel component. Right, so if I solve the problem just as I did before with the variations that are needed here. It's still the case that the power from the applied force, ultimately the engine of the car, is equal to the force applied multiplied by the speed at which it's moving, multiplied by the cos of the beta angle. And don't confuse alpha and beta here. Alpha is the angle of the incline, which was 15 degrees. Beta is actually still going to be 0 degrees because the applied force is moving towards the top of the incline, and it's moving towards the top of the incline. So if it moves in the same direction as the force, it doesn't matter which way that actually is. It's the angle between. So let's kind of be a bit sloppy here. I'm forgiving on stuff like this. Cos of beta, cross it out, and maybe I'll just put a reference here that this is numerically equal to 1. So cos of 0 is 1. Power applied is equal to the applied force. Now remember, in size, we're saying that the applied force is the same size as the rolling resistance alongside its helper force of gravity parallel component. So together, that is equal to the applied force times the speed times the cos of beta, which I've already kind of now neglected because it's just numerically 1. Power applied is equal to the force of rolling resistance, which is going to be mu times the normal force. Well, again, if you think back to our inclined plane chapter, the normal force would have to, because there is no acceleration, well, at all, but in particular along this line, it would have to match the size of the force of gravity perpendicular. So this is a nice review from our earlier unit. So it is mu times the normal force, but the normal force itself is going to be equal to mg cos of alpha. So this is, again, mu times the normal force. The normal force is equal to itself, the force of gravity perpendicular component. And I just realized I closed that bracket too soon. So there's the force of rolling resistance, add the force of gravity parallel component, mg sine of alpha. So everything you see in brackets there, don't lose track of what we're doing. Everything that I just wrote in brackets ultimately is my determination of the applied force. And yeah, you know what? A lot of students seem to prefer, often at least, to do these little calculations on the side, like calculating a numeric value, for example, of the applied force. If you did that, it's totally okay. It would be fine, assuming you're doing it correctly, of course. But hopefully you can see, and I'm hoping you're getting more comfortable as we proceed into our course, working with algebra this way. In the end, especially once you gain that level of proficiency, it's actually way faster to do it this way. And it's nice if you make a mistake, as I did in a recent problem, it's much easier to fix if you work algebraically as much as you can. Okay, so just to finish this off here, all of this is multiplied by the speed. I think I'm ready to just put values in. So mu was 0.08, I think. It's always tricky for me because I have to scroll back. Yeah. Oh, and while I'm up here, 750 at 8.3. Okay, I'll try to remember as much of that as I can. Mass was, that's how, okay, I'm focused on the physics. Oh yeah, 750. 750 multiplied by g, 9.8, multiplied by the cos of, I remember this one, 15 degrees, add m again, so there's 750, g is 9.8, and then sine of 15 degrees once again. So all of that is the applied force, and then of course multiplied by the speed of 8.333, squeeze one more in there for 5 sig figs, right? It was 8.33, yeah. Calculator time, power applied. Now, in case you didn't notice me doing this in previous videos, I don't actually enter on my calculator all of these brackets. If I'm just taking a number multiplied by a number, I mean, like when we're writing it on paper, brackets are really kind of nice for that. On my calculator, I'm actually just going to type in a 0.08 multiplied by this number, again, times this number. I'm definitely not going to enter the brackets in the identical way that you see them, although on some calculators you could. I've noticed variations in models and brands. Some calculators have little peculiarities to them, which is yet another reason why you should always use like the same model of calculator, preferably your own. So on my calculator, I'm going to enter I'm going to start with open bracket. I do need this bracket on my calculator because it's ultimately serving to hold all of this together, especially since there's two separate terms in there. Those are not optional brackets. So I've just hit open bracket on my calculator. I'm entering now the following. 0.08 times, literally the times button, 750 times 9.8. Probably don't need this times on my calculator, but I have a bad habit of it. Cosine 15, add 750 times 9.8 times sine 15, and I now close my bracket. So I've entered everything that you see within the brackets. I'm going to continue by hitting times 8.3333, and I can hit equals, and assuming I haven't screwed that up somewhere that I'm not aware of, I should get the right answer. The answer that I am getting is, I'm just going to record it to 3 sig figs. Its calculator says 63895, etc. I'm just going to say 639, and then 2 zeros, yeah. There we go. So 63,900 watts. And that should do it for part B. A quick comparison here, just to see if this makes kind of sense to you. Let's call this roughly 64,000, just in the ballpark of 64,000. In part A, we had in the ballpark of like 5,000. That's a pretty dramatic difference here in part A versus part B. And of course, if you've driven a car, you will have direct experience, and even if just being the passenger in a car, you can have awareness that, yeah, driving up a hill, the engine does have to work harder. And by the way, 15 degrees might not sound like a very large angle. If we're talking about a road surface that's inclined at 15 degrees, that would be a very steep road. In fact, you won't ordinarily come across, certainly nothing like around Winnipeg, Manitoba. Maybe in a parking garage somewhere, like if you have to go from one level of the parquet to the next level, perhaps there. I'm not even sure how steep those would be, but this is definitely not just like a little hill in Winnipeg for sure. Any case, yeah, cars have to work harder to go up the hill. Who'd have thought? Moving on. Number 3. Okay, so when training, a person that has a mass of 64 kilograms climbs up 47 stairs in a time of 1 minute. Each stair involves moving their center of mass. Center of mass is something that I don't think that we've used that term before. So I'm going to say that an understanding of it for this question is not needed, but just to be formal about it, your person here is a complicated shaped object, right? They have legs and arms and head. They have various body parts, each of which can move. The reference to center of mass is basically saying you don't need to factor in for all of those parts. The person taken as a whole has basically moved. Okay, so that's all that the reference to center mass is. In 30S, I'm going to leave it as that. If there's any AP students listening to this, because this is a 30S worksheet, but if there are any AP students listening to it, center mass is something that we're going to look at in depth very soon, in fact. It's coming up in the course. So, with that said, let's just do it. There is a person that has a mass of 64 kilograms. They climb up 47 stairs. Yeah, okay, so how about if we, again, I'm thinking back to that very first question that we did where I gave the two options, the powers, force times speed versus work divided by time. For no good reason, I'm just going to choose the work divided by time option for this one. Either one would work. So thinking along the lines of work divided by time, I'm going to want to know the work that this person had to do. Okay, so, I should mention this too for the AP students. Okay, AP students, this question here is using what I'm going to describe as a traditional, let's say, approach to the idea of work. This is very, very, very common at the high school level, and it is also very, very common in a lot of like intro university courses, but the College Board AP program does not use it. So AP students, for reasons involving systems and internal, external forces, technically, I would have to say that this person does not do work at all. They're transforming energy within the system, but they're not doing work, because work has a very subtle kind of complexity to it that we're only going to explore at the AP level. So AP students, be warned, this is really, the solution I'm about to write is not quite compatible with the College Board approach to work and energy. Okay, so with that said, I'm just going to proceed. So they're going to, let's say that they start at a, well, actually, let's not even bother saying that they start at a height. Let's just say that they travel a distance. Oh, actually, hang on. Yeah, okay. I'm going to keep it simple. Let's say that they start at a height of 0, and they end at a height that is ultimately, well, 47 stairs higher. So their any height is going to be 47 stairs, each of which is 20.7 centimeters, so 0.207 meters. So just multiplying the step height by the count of steps, so 47 times 0.207. So they have just basically elevated their body to a height of 9.729 meters. All right, now the reason, if you're curious, the reason I was reluctant to write a distance there is because technically I don't know what distance they're traveling. Depending on how steep the stairs are, the distance, which by the way is length of path traveled, could be different. Think of it this way, if this was a ladder instead of stairs, and the ladder was just perfectly vertical, okay, fine. Then this could legitimately be described as their distance if they went straight up. But if they're traveling kind of along a set of stairs, which I'm not really drawing in here, and they elevate themselves to this higher height, okay, so that's like h prime here, the distance that they traveled would technically not, well, not even technically, it would just absolutely not be 9.729. So that's why I am not going to identify that as a distance. Okay, so yeah, I don't think that diagram is really needed. It was just an aside. Okay, so how much work did they do? Well, let's kind of fall back into our m prime equals m plus network NC, which hasn't made an appearance yet on this worksheet. So here's our first appearance. K prime plus u gravity prime equal to k plus u gravity plus the network that was done by non-conservative forces, which we're just kind of giving them a pass on this. That we're just going to say that this is the person and 30s physics, leave it as that. What can I cross out here? They started at a height of 0, so I don't need that. Kinetic energy and kinetic energy prime, again, for reasons that were in depth explained in the previous worksheets, I can cross those out because they're both equal to the same value if you think of them just maintaining the motion throughout, or you could think of them as effectively both being 0, with a person starting at rest, then climbing the stairs, and then coming to rest again. No matter how you do it, you can legitimately cross them both out, which means that the net work that was done by non-conservative forces is equal to the gravitational potential energy they end up with, which is equal to mg height that they end up with, which is equal to, you know what, let's just leave it as that. I'll take advantage of that algebra thing that I just told you. I remember in the last problem I was saying, you could calculate numbers along the way, but you don't actually have to. Let's just leave it as that. Let's leave it algebraic. That is the work that they would have to do. Why do I need that work? Because I'm trying to find the power associated with this applied force. And by the way, 30s, we're calling this the work that was done by the applied force. There were no other forces, enabling this person to go up the stairs, let's say. So if you want the power associated with the applied force, just take the work that was done by the applied force and divide it by the time that it took to do that work. And we know that it took that person, in a minute, right? Don't miss little things like that. In a minute, so the time is 60 seconds. So if they did this much work in a time of 60, let's keep it algebraic one step longer, in a time of 60 seconds, then this will just do it. the m is 64. I'm now putting numbers in. 9.8 times the distance of, h prime of, right there, 9.7-ish. 29. All of which is over that minute, 60 seconds. So it's calculator time again. 64 times 9.8 times 9.729. If I hit equals right now, this is the number on my calculator, 6102, decimal, etc. I mean, that was just the numerator. That's the work that was done. So if I had calculated a value, that's what it would have been, roughly 6,100 joules. But I'm just going to continue on my calculator, divide 60 to get my final answer to this question. The one thing I was really after here, the power is 100 and I'll round it off to 2 watts. If you care, and you have no need to care right here, but the calculator right now says 101.7, etc. But 3 sig figs, we're good. So that's the power associated with the applied force. And, you know, a person climbing stairs, especially if you try to do it quickly, that's very tiring. It's difficult. One of the reasons it's so difficult is because it takes a lot of energy, and if you're doing it quickly, you need to do that at a very high rate of doing work, right? The work is being done quickly, and that's all that power is. How quickly are you doing your work? If you climbed up the stairs, okay, so this was like in 1 minute. Let's say that you instead traveled up the same flight of stairs, but at a reduced speed. Like, let's just say it takes you like 10 minutes to climb up the stairs for whatever reason. So instead of 1 minute, 10 minutes, to be clear, you'd still be doing the same amount of work. The numerator would not have changed just because of saying 10 minutes now. So you're doing the same work, but you'd be doing it, there'd be a 10 times as much, so, you know, 10 times 60, and that would have reduced our power literally by a factor of 10 to 10 decimal 2 watts. And hopefully that just makes sense on its own, because if you leisurely climbed up the stairs, it just seems like it's less tiring, right? Because your body has that time to recover, or not even recover. It's probably not going to be even stressed in the first place. But anyway, that's the whole concept of power. Power is not a measure of like what you're accomplishing in the end. It's a measure of how quickly you're getting it done, independent really of how much you did in the end. Okay. In fact, a related question, what if I said, okay, so in climbing only up the first 20 stairs, but let's say this person moved as described, but let me just on the side ask another question. What if I said, yeah, they did that. They climbed the stairs in 60 seconds, you know, all of 47 stairs. So what was their power for just the first 20 stairs? So if you really understand this concept, hopefully you already know the answer. Just the first 20 stairs? The answer is 102 watts. It's no different. Because they wouldn't have got, actually let's focus on this, they wouldn't have gotten all the way up yet, but they wouldn't be all the way through their 60 seconds yet. In fact, because they're going at a constant speed, definitely what I'm assuming at least, the time that is only a fraction and the height that's only a fraction would actually come up to the exact same answer, which should make sense independent of that equation, because the rate at which you're doing work, if you're climbing up the stairs at a constant rate at least, you're doing work at a constant rate. Your power is constant. Okay, moving on. Number 4. Hi, Molly. How are you doing? Molly has just arrived at the airport. Molly, this is not the time for travel. I'm a little disappointed, I have to say. Arrived at the airport, dragging her suitcase to the luggage check-in desk. She pulls on the strap with that much force, an angle of that much, displacing that far, time given. Okay, so just a variation on the kind of thing we've been doing. So this time there is certainly a level surface, the ground at the airport, the floor. There's some kind of a luggage, generic box. And what's happening to it here is that it has a force being applied. So let's just kind of sketch it in like this. This is the applied force at an angle of 35 degrees to the horizontal. Okay, so 35 degrees, maybe something like that. Again, never worried about drawing it to the correct scale. So yeah, don't grab a protractor. I have no interest in how accurate that is right now. So let's just get our numbers here. Force applied was given as 190 newtons at an angle of, actually, you know what, hang on, let me do this. There's nothing wrong with it, but how about if I do this? Theta. Theta is equal to 35 degrees. Why not? And I'm not even thinking of the chapter that we're in right now. That I could have done that way back earlier in the course when we were just talking about forces at that point. Theta, why not? Let's just give that a try. So 35 degrees to the horizontal, and it displaces 45 meters. Don't worry about the word displacing here. I mean, it just moved that far. That's how far it moved. So displace, distance, in a context like this, we're good. So I can think of that as the distance. 45 meters to the desk. It takes her a timing of 95 seconds to get to the desk. What was the power associated with this applied force? Question mark. Okay, well, this one's actually set up really, really, really nicely. Before you start resolving into components and normal force and gravity and all of that stuff, just sit back and realize we're being handed everything we need quite nicely. Since the luggage is just moving to the right, I mean, that's the whole setup that I've drawn here, this 35-degree angle can also be interpreted as the beta angle. So when I first drew it, I was thinking of it as just some generic angle, and it's only later upon thinking it through deeper that I can validly say, hey, wait a minute, that angle can be understood to be the beta angle, the angle between the direction of the force and the direction of the motion. That's beta. Okay, now for the record, theta I use as a more generic letter for angles in any configuration. It's only going to be occasionally that there's going to be this, the sameness to them. Theta is a generic angle, and let's reserve its use for that. Let's continue to use beta as a special angle for a special symbol for a special angle. Okay, and in this case, they were one and the same, but not always. So if you want the, if you want the power by the applied force, highlighter. Let's see. We have a distance and a time here, so that's practically just as good as having a speed. I've got a force and a beta angle. Let's just dive right into this. The power associated with the applied force is the applied force multiplied by the speed multiplied by the cos of the beta angle. And of course, the speed itself can be understood to be the distance traveled divided by the time it took to travel that distance. So that is the speed right there, kind of just built in, multiplied by, well, the cos of beta, right? By the way, a quick little math thing here. I wrote it this way just visually because I wanted you to understand, distance divided by time is the speed. But mathematically, you could extend that. It makes no difference at all. So I'll just do it that way because it looks more conventional this way, I guess. That's why I'm going to do it. Putting the numbers in, the applied force was 190. The distance moved was 45. Okay, the cosine of the angle was 35 degrees, all of which is over the timing of 95 seconds. So the power associated with the applied force, 190 multiplied by 45 multiplied by the cos of 35 divided by 95. And if I had done that divide 95 a little earlier, it wouldn't have mattered. It would have come to the same answer. So I'm getting 73.7 watts to 3 sig figs. There you go. So Molly, again, a little disappointed you're doing it, but good on you that you're getting some work done, right? Okay, let's move on. Number 5. Toboggan kicked on a flat frozen pond acquires a speed of that. Okay, so we kick it. If I'm reading this for the first time ever, and in truth I'm not, I did read this question before, but if I was reading this question for the first time, I would immediately start to organize my thoughts. Like, okay, so there was a kick. One of the questions that I would probably start to focus on is this question really wanting to investigate the kick itself? Like, should I be thinking like, well, it was sitting there initially at rest, so V initial of 0, but then kick, and as a consequence of the kick, maybe I could think of this as V final equal to 3.9 meters per second. If we were investigating the kick itself, like, how much force is needed or how much force was that kick applying to the toboggan, then that would probably be a good way to go, right? The V initial of 0, the V final of that, if we were investigating that kick itself. The movement of the toboggan while it's still in contact with the person's foot. But if we keep reading, I think we're gonna change our mind that was a good idea. The coefficient of friction between the pond and the toboggan is given. Determine the distance which the toboggan slides before coming to rest. Okay, now in a question like this, and again, this is kind of more familiarity with questions. The real intent of this question, and I'll just add in a little bit of clarification here. This really is after being kicked. Okay, so in a textbook problem especially, you have to have these interpretations. So we're not really going to worry about how far the toboggan moved while it was still in contact with the foot. Now, in case you're wondering, like, how did you know to make that assumption? Really, it's the absence of any information about the kick. I don't know how much time that the foot was actively pushing the toboggan. I don't know over what little distance that the foot was actively pushing the toboggan. This question really, really begins with it in motion. Okay, so that lead up, the kick itself is in effect, the history prior to what I'm really interested in. What I'm really interested in here is that there was a toboggan. I'm not going to draw an applied force. I'm actually thinking of right now, this thing is already moving. It's already moving with a speed of, well, an initial speed, but I'm going to use prime notation here. So V of 3.9 meters per second. And what's going to happen is this thing is going to slow down, slow down, slow down, slow down, slow down. At some point, it's going to stop. So I'll call V prime equal to 0. Okay. So, organizing things, the mass is given 4.9 kilograms. Requires a speed, so that initial speed, I already wrote it in there, but I'll add it in here just for clarity. 3.9 meters per second, leading to a V prime of 0. The question is, if there is a coefficient of 0.13, then determine the distance which the toboggan slides before coming to a rest. So over what distance did it go? So this is a question that, honestly, you don't need anything to do with work and power and energy. You really could use the methods that we learned earlier in the course about forces and Newton's laws, and of course kinematics. This could be totally solved that way. And if this was a test, for the record, correct physics gets full credit. Okay, if you're doing fully correct physics and getting the correct answer to what you were asked to find, any correct method would be accepted as full credit. So if your instinct here was to just use that method, then that's okay, like long-term okay. But how about if we kind of add a little qualifier, since we're still learning this unit? It would be awesome if we avoid that just for the sake of practice. And remember that there are plenty of situations in which this work approach is really needed. So this is not one of those cases that it's really needed, but it's good practice for us. So I'm going to deliberately avoid solving it that older way, the way that we learned earlier in the course. I'm going to kind of require myself to use a work energy approach. Doing so, let's get to work. There is a normal force, so that's not to say that what we learned earlier is irrelevant. This is still relevant. This will be equal to the force of gravity in this case because it's not accelerating vertically. There's no other vertical forces. So, yeah, the normal force is not always equal to mg, but it is equal to mg in this case. And there is a force of friction that is causing it to slow down as it moves. And remember, there's no applied force because I'm considering the moment after it was kicked. If you had an applied force in here, then you really wouldn't be up to your starting speed, at least what I'm calling the starting speed, of 3.9 meters per second yet. So hopefully that's clear from, kind of what I've just explained. Okay, so if I want the distance, and I'm kind of like forcing myself to use a work energy approach, I'm thinking of force times distance, right? Work is force times distance. So let's do that. The mechanical energy that this thing's going to end up with over here is equal to the mechanical energy it started with at this moment in time that I'm considering, plus the net work that was done along the way by non-conservative forces. So let's just kind of expand that the usual way. K prime plus U gravity prime equal to K plus U gravity plus the net work done by non-conservative forces. Okay, nobody asked me, but here's a question that I'll throw out and answer. Mr. Panis, why do you even bother to write that? I mean, because every time you write that, the very next line is this line, like every time. Wouldn't we just save ourselves the effort? Why bother even writing that? Suppose that somebody asked me that question. Here's how I would answer it. Yes, it's true that in every instance so far that has been the case. You know, this line led to this line. True. It will not remain true. In the future, especially in 40S physics or the AP physics for that matter, erase that one, we will be looking at additional forms of energy. So I probably should explain this at some point. Now is as good of a time as any. Each time I write this equation, I'm giving a moment's thought to what forms of energy are even relevant and present in the situation. And right now we're kind of limited because we've only started this unit. So, I mean, kinetic energy and gravitational potential energy are the only two we've been introduced to, kind of, you know, in that mathematical level at least. So, yeah, this is becoming routine. But if you want to get good at physics, like seriously, if you want to get good at physics, don't settle for routines. Always dig deeper for an understanding. And that's the reason I'm doing this. In this question, there was nothing else like energy interesting going on here. In 40S physics, just to give a little heads up here, in 40S physics, it might be the case that a question similar to this, all of a sudden, let me just kind of temporarily add this just as if it were part of the problem. All of a sudden, let's say that you have an electric charge on this thing, like it's positively charged for some reason. Yeah, electricity is investigated in grade 12 physics, 40S physics. So if there was like a positive charge on this thing, and for whatever reason over here, there's some other object that was positively charged, then these things would be repelling each other, and they would have an additional form of energy beyond what we've been learning about. There would additionally be, just to kind of throw this in here, there'd be an electric potential energy. And I'm not trying to teach that right now. I'm just trying to give you a little heads up. This is the reason why I write this equation, because in the next line, I can kind of tailor that equation to the problem that I'm doing. And right now in 30S physics, I'm kind of limited, but keep your options open for the future. Okay, just kind of clear that out there. There we go. That little yellow circle's not wanting to go away for some reason. So, moving back into this. Okay, so what can I cross out here? Because that is also kind of part of the routine. Don't settle for routines, I just said. But this makes sense. I mean, I can cross out things that are equal to 0, right? So, K prime, well, it comes to a rest. It comes to stop. U gravity, prime and U gravity, well, if we just think of that as the reference height, then it had 0 height at both places. So I could cross them out for reasons of 0, or, as before, for reasons of they're the same. I mean, even if they weren't 0, they're the same. So you could subtract them, if not, call them 0. Wow, okay, that means that on the left side of the equation there is 0. And that's correct. Don't be bothered by that. 0 is equal to the kinetic energy it started with plus the net work that it was done along the way. In fact, let's modify that. What did work along the way? Were there any non-conservative forces doing work? Well, there are actually 2 non-conservative forces present. Force of gravity is conservative, so that's kind of in a separate category. Don't worry, we've already given gravity its consideration. Okay, so gravity is already kind of taken care of and ended up being neglected anyway. So what about these two? The force of friction, Yeah, it definitely did non-zero work. It did exert a force over this distance, and notably in that case, the beta angle will be 180 degrees because the force of friction is, to the left, and yet it's moving to the right. So there's a 180 degree angle between the force of friction and the distance, or the motion. Not so for the normal force. The normal force is perpendicular to the motion, and so does zero work. So with that thought through, I'm prepared to say that the only non-conservative force that did any work here was the work done by friction. Now this actually makes sense. The energy that you end with, nothing, is equal to the energy that you started with. Actually, we did start with something. We had energy. We had kinetic energy. So how did we end up with nothing if we started with something? Well, don't forget what this means. What you end up with is equal to what you started with plus any transfer of energy that happened. If you were given energy, you would have more than you started with, but you can have energy taken away from you. So yeah, you can end up with less than you started with. So that is exactly what happened here. That negative work done by friction removed the energy. So in fact, let's do it this way. Let's just solve for the work done by friction. So I don't even need a reference to net, sorry. It's just the work done by friction. It was the one and only one thing that did work. So the work done by friction, let's imagine subtracting k to the other side of the equation, even though it's kind of on the right side here. I'd have to have 0 subtract k equal to the work done by friction, and I've written it in a more conventional form here. The thing I'm looking for is on the left. Yes, so the negative of the kinetic energy. Now, for the record, kinetic energy is positive, but we're looking at the negative of that kinetic energy. So 1/2 mv that you started at squared. That's how much work friction had to do. So the work done by friction is negative of 0.5, 4.9, 3.9. Okay, 4.9, 3.9 squared, right? To double check that, 4.9 mass, 3. Yeah, looks good. So the work done by friction is equal to, calculator is right here, hiding. Okay, so negative 0.5 times 4.9 times, don't forget the square, 3.9 squared. I'm getting negative 37.3 joules. And that would be the answer here. So the work done, oh, actually, hang on, just double check. Yeah, we're just looking for the work, not the power. We were only asked for the work. No, hang on. I've lost track of what we were ultimately trying to find here. This is my error, especially since I'm scrolling back and forth. I fail to remember what I was looking for. Much easier to do this on like actual paper. So this is not like incorrect, but it really is not what we're looking for. And that again is just my error. So I'm gonna actually, it's probably easiest to just kind of go back a little bit. So let's go back to this stage here. So everything that I wrote to this point, I think is still fine. So let's just slip this in. The work done by friction can itself be calculated as the force of friction times the distance moved multiplied by the cosine of the angle as it pertains to friction. Okay, so there's the distance that we're looking for. Okay, so that means that we need to find force of friction. So how much was the force of friction? By now, this is very familiar. We've got the coefficient, we've got the normal force equal to the force of gravity. So in the sake of keeping things, no longer than they need to be, because I know that it's already long, mu times the normal force, which is equal to the force of gravity in this situation, distance cosine of beta equal to basically the same, right? So negative 0.5, 4.9. I should have kept this algebraic a little bit longer, so it's a bit of a mishmash, but so be it. Distance is equal to negative 0.5, 4.9, 3.9 squared, all of which is over mu. And again, I'm just going to put the numbers in now, sorry. Mu is 0.13. M was 4.9. Oh yeah, because we already had that here. Yes. Yeah, okay, the mass would have canceled. See, and again, it's little things like that. If I had kept it algebraic a little bit longer, I would have seen that a little sooner. The masses will ultimately cancel. So this is a bit of a botch up on my part, but it's probably okay. So there's the distance equal to that. Oh, and times the cosine of 180 degrees, right? Friction was to the left while it moved to the right. 180. By the way, that cos of 180 is what's going to make my answer positive, which is awesome because distances can't even physically be negative. So notice the way no trickery on my part. The answer is mathematically, as it needs to be, positive. So distance is equal to, I'll just grab my calculator on this one. Okay, so, hey, on my calculator, I'm going to take a shortcut. Those 4.9s cancel, so I'm not even going to bother with them. So on my calculator, oh, and the negative is going to cancel the cos 180 in the fact that it's like positive. So on my calculator, I'm just going to punch in the following. 3.9 squared divided by 0.13 and also divided by 4.9. Okay. So I'm getting an answer of 23 rounded off to 9 meters. Hopefully that's correct. If I make a mistake, because I'll verify my answers after recording. If I make a mistake, I'll do something about it. Either overlay some text pointing out my goof, or re-recording if there's a really major catastrophe. Hopefully not. Number 6, Matthew. Hey Matthew, how are you doing? Hopefully you're okay. Starts from rest on top of a 10.45 meter high sledding hill. He slides 27-degree angle, etc., etc. Okay, so there's a lot going on here. So let's start with a diagram. There's this hill. So it's sliding down an incline and then across a flat plateau. So the reference to a flat plateau just means that the ground levels off at the bottom of the hill. So it just kind of, in fact, here, I'll draw it. So it kind of slants down for a little while, and then we're just going to assume nice and, simplistically, it then levels to be horizontal. So here is Matthew, which is looking very much like a box. Okay. Matthew starts from rest. Okay, so let's say that V is equal to 0. On top of a 10.45 meter high sledding hill. Okay, so that's really nice. So if I call this the reference height, and I think he ends up there, so I'll just do that. That means that he started with a height that was given to me rather conveniently. I didn't have to do any trig or anything. Yeah, 10.45 meters. He slides down the 27-degree incline. So from the horizontal here, this angle alpha, the inclined plane angle, is 27 degrees. It slides down and then across the flat plateau. The coefficient of friction between the sled and the snow is 0.14, so coefficient is 0.14 for both the hill and the plateau. So there's a continuous, like the same kind of surface here. It's not like it changes all of a sudden. It was like snow, concrete. It's snow everywhere. So the same coefficient of friction. They have a combined mass, so mass of the box in my diagram is 20. Holy jeez. This is literally my first time looking at this problem. Okay, this is not grade 11, Matthew. This is a very small child, Matthew. Or and again, it could have been Matthew a long time ago, come to think of it. So, I don't know. It's Mr. Dawson's question. But 27.5 kilograms. Okay, now, even though we live in Canada and we're supposed to be metric, if you care, 27.5 times... The conversion there is 4.54, I think. So this is 124 pounds. That's actually not as crazy as I thought, for the sled and Matthew. Okay, so depending on the sled, I don't know. The sled might be, who knows, depending on what kind of sled. Okay, maybe it's not like crazy, but that's pretty small still, though. So, like, we're talking roughly 125 pounds for the person named Matthew, whoever that person is, and the sled combined. Okay, but we'll just use the numbers as given. 27.5 kilograms. Determine the distance which Matthew will slide along the level surface. So that's what we're trying to find. Find the distance, because at some point, let's just kind of draw in that point, at some point he's going to stop. Okay, before coming to a complete stop. By the way, I'm definitely going to do this algebraically, and I bet you, in fact, I'm thinking ahead here, the mass is almost certainly going to cancel out here. Quite sure, but I'll let the math take care of that for me. Okay, so we want to know the distance that I traveled, and again, I'm going to invoke a kind of a restriction on myself, and I would encourage you to do the same. Let's only use, or at least as much as possible, let's use the recent physics of work and energy. Obviously, we're still using some inclined plane physics and stuff like that, but wherever possible, let's try to maximize our use of this newer topic. So I will avoid using kinematics if I can instead use some work energy approach. And that's an artificial restriction, to be clear. I'm just doing that for maximizing my practice with this new topic. Okay. So here's a bit of a concern in this question, because there is this like two-part motion here. I am, even in this new approach, I'm going to need a two-part approach, because the force of friction is going to change size. Actually, that's the main concern I have. As he slides down here, the normal force is only going to match that force of gravity perpendicular component. But once he's on the level portion, the normal force will equal to the force of gravity. But you know what? Rather than get ahead of myself, let's actually let this happen more kind of like organically. I'm going to give myself a little bit of extra space there, so because I'm thinking of adding to the diagram right away. So I'll just put it here. Height equal to 10.45 meters. Okay, so while he's on the incline, there is very much a force of gravity parallel component. There's a force of gravity perpendicular component. There's a normal force, and there is a force of friction. In this case, it would be a kinetic friction because the toboggan is just sliding. Okay, now while he's on the incline, notice that these two will balance each other, right? Because there's no acceleration along this line. So the normal force will be equal to the force of gravity perpendicular component while on the incline. That's going to change though, because as soon as he enters the level portion, so let's just say he's still moving along, but just at some point, just to make my diagram clear, at some point there's going to be a normal force, a force of gravity, and I'm not on an inclined plane right now, I'm just thinking of the conventional force of gravity, and of course friction will be this way now. So force of friction. So friction was, opposite of the movement throughout, although I'm reluctant to say that that's, always true, but in this case it certainly was. And we want to know how far he slides along this portion. Okay. Let's see if I can come up with, I'm thinking of doing it one way. I think it's going to be a good way. We'll see if it's maybe arguably the best way. I don't know. So let's give this a try. I am going to try, okay, let's try this. I'm going to do this kind of in one shot. I'm going to see if I can really flex my physics muscles here, especially with that M prime thing that I like to use so much. Let's just think of this as the end, and let's think of this as the start. And at least for the moment, I'm not even going to worry about like part one, part two, but that will happen within. Do you have to do it the exact same way that I'm about to do it? Of course not. If you wanted to do a part one and, kind of figure out the speed at this point, and then kind of reset into a part two where that end speed of part one becomes the initial speed of part two, that would be a good way to go. There'd be nothing wrong with that. I'm going to avoid that, only so that you can maybe learn something from this kind of different approach I'm going to take. I would argue that in the end, my approach that I'm about to use is going to be probably a little bit more complicated, but not a lot. But in the end, it would actually be a super efficient way to do it. And maybe you'll see that by the time I'm done. So by the time you get down there, okay, so let's just kind of return to this. By the time you get to the very, very, very end, and I'm thinking of you have stopped at the bottom, the mechanical energy you end with better be equal to the mechanical energy you started with, when you were up here, allowing for the fact that maybe, just maybe, non-conservative forces did work along the way. Okay, so let's see what our kind of this standard approach does for us. K prime plus U gravity prime equal to K plus U gravity plus, Okay, let's kind of think about this for a second. Did any non-conservative forces do work? Well, even though I've got it in components, that's the force of gravity, so ignore the force of gravity, for this part of the equation at least, for the network non-conservative. That only leaves a normal force and also a force of friction. Notice how the normal force, even though there was a shift, like it was pointing one way, not vertical, and then, oh, yes, it's vertical. Notice that it remained 90 degrees to the motion the whole time. Here, the motion is down the ramp, and that's perpendicular to it. Here, the motion is to the right, and that's perpendicular to it. The normal force did not do any work at all. And by the way, it's not a universal rule that the normal force is incapable of doing work. Not true. But it definitely is true in this situation. Meanwhile, the force of friction, if we just kind of pay extra attention to it right now, let's just hone our attention there. Even though, again, the force of friction changed size at that kind of transition point, it actually remained opposite of the motion throughout the whole movement. So the force of friction had a beta angle, if you will, of 180 degrees, and that actually never changed throughout the whole movement. It was opposite of the motion the whole time. So it did non-zero work. In fact, it did negative work. So the only force that did work was the non-conservative force that did work here was the force of friction. So what can I cross out? Anything equal to 0 here? Well, by the time we're here, we have stopped. And we're at the bottom, where I've kind of set my reference height. So on the left side of the equation, I literally have 0, kind of like I had before. What about at the start? Well, at the very, 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 very start, Matthew wasn't yet moving, right? He was just stationary up here, and then he began to slide. So he had no kinetic energy at the very, very, very start. And you are seeing it right now. Like this is the versatility of this work energy approach. Yes, there was kinetic energy at various points along the way. Like he was moving here, he was moving here. He had kinetic energy at lots, like in fact, throughout this entire motion, he had kinetic energy. But it doesn't matter if we're only comparing the end point to the starting point. It is true that he ends with no mechanical energy, and it's true that at the very start he only had this form of energy. So this is why I was kind of thinking, like, this is going to be awesome. This is going to work really well. There is a complexity coming up, though, and I'll get there right. In fact, well, I'll do this first. So let's just kind of do U gravity plus the work done by friction. Okay, now here's the complexity. The work, even though friction is like a singular force and it singular, like on its own, it's the one thing that did work here. I do have to break it into the two parts, though, because as I kind of hinted at before, the force of friction does not have a constant size throughout the entire motion. If somehow the friction had maintained a constant magnitude, then I would be okay with just kind of doing this in one shot. But because friction changed size, I'm going to need to kind of deal with that. So how about if I do it this way? 0 is equal to U gravity plus, because friction did work in kind of this weird way, I'll use my colors of green and red to be consistent with my diagram. Let's think of it while it was on the hill, work did friction part 1, while on the incline, in other words. Plus, friction did a little extra work, actually, probably considerable extra work, while it was on the level surface, or while Matthew was on the level surface. So, yeah, friction did work, but I have to break it into two parts because of that change that occurred at the transition. Okay, let's see here. That means, and let's not lose track of what I'm trying to ultimately find. Let's label that. I'm trying to find what I can now call distance part 2. Yeah, don't lose track of what we're ultimately after. So distance part 2, so kind of within here, I'm going to need to know that. Hey, a quick calculation might be in order right now. What was distance part 1? Okay, so if you just think of this, our favorite shape in the whole world, at least my favorite shape in the whole world, a right triangle. Distance part 1, how long the slope was, is something I can find with a quick bit of trig. I'll just do that on the side here. Let's see here. I have the opposite. I'm looking for the hypotenuse, so sine. So the sine of alpha is equal to opposite, which, by the way, is not this force. It's the height, right? So is equal to the height. In fact, I'll just put the number in 10.45 over, oh, in fact, if I'm putting numbers in, let's put sine of the actual angle, which was 27 degrees. I have that written here. So 27 degrees. No, sorry, my mistake. Lost track of where it was. Sine of 27 degrees is equal to opposite, which is effectively the height, divided by the distance moved in part 1. Yeah, so the distance moved in part 1, I'll just kind of compute this in one shot. That would be 10.45 divided by the sine 27. So 23 and a bit. 23.018 meters. Yeah, there we go. 23.018 meters, 5 sig figs, my usual preference. Okay, going back into here, 0 is equal to mgh plus the full green color coding, something you definitely do not need to do, of course. Force of friction in part 1, because remember the size changes. The distance moved in part 1 multiplied by the cosine of beta as it pertains to friction, which actually remained 180 degrees throughout. So I won't even bother with a 1 on that one, but you could. Add part 2 work done by friction. So that's going to be the force of friction in part 2. The distance moved in part 2, which is what I'm after, don't forget, multiplied by the cos of beta in part 2 for friction, but it was 180 still. So let's do ourselves the favor of realizing that since this is just -1, cos of 180, and this is also -1, in effect, I can rewrite this. Because this is a negative term, let's imagine that we're just going to add it to the left side of the equation. So what you see in green, including that cos of beta, is basically negative. So left side of the equation, it shows up. Force of friction in part 1, distance part 1. I've already got the cos of beta, and that's why I switched it over to the other side of the equation. Hopefully you'll see what I mean right away, if not yet. mgh. The green term has also already been added to the other side. The red term, I do like to use kind of color coding to help when I'm trying to explain this kind of math. Since this is a negative value here, it effectively is going to turn the addition into subtraction. So let's just do it that way. Force of friction, distance, part 2. And again, I've already kind of incorporated that cosine of the angle. So that's it. That's what it's kind of collapsed down to. What am I looking for? What am I looking for? You know what? Again, this is me. This is a small goof, not a big one, because this is not incorrect. What I really aimed to do was to get this to the other side, but I kind of lost track of which one it was which. So, okay, rather than erase anything, how about if I just say, oops, what I meant to say, and I'll just, as if I'm doing it now, I really wanted the red term on the left. So force of friction in part 2. Distance in part 2, so let's like add that to the left side, and I guess the part 1 just went for a joyride because it's going to come right back, so let's subtract it back where it already was, sorry. Force of friction part 1, distance part 1. Okay. Now, left side of the equation. Left side of the equation is going to be force of friction when it was on the level surface, mu times the normal force. How big is the normal force? Well, vertically, same situation as we often come across. Not always, but often. In fact, right away it won't be. The normal force in part 2, in fact, let's even write it that way. The normal force in part 2 is equal to m times g. So this is going to be mu times the normal force in part 2, which is m times g, times the distance moved. And that is equal to mg height minus force of friction part 1, which is mu times the normal force in part 1. How big is the normal force in part 1? Well, as we've seen before, it's going to balance the force of gravity perpendicular. So that's going to be mg cosine of the angle of the incline. So mu times the normal force. So again, notice how the normal force was just equal to the force of gravity in part 2, but it's equal to a component of it in part 1. Okay, I think I've got everything, I hope. Okay, hey, look at this. My prediction is true, or was my prediction from earlier is true. There's a mass in every single term here. Mass, mass, mass. So I can actually divide m right out of this whole equation. So even though I knew the value it was given as 27.5, turns out that if we had given you a different value, like if this was 1,000 kilograms, it ultimately in the end would not have affected our answer. And by the way, in case up until now you've been thinking like, whoa, this is like really complicated, and I'm hoping you're not. I'm hoping you're really following along here. It's little things like this that you would quite probably miss if you're just kind of doing little teeny tiny calculations. Like I guess I did it here because this was just like basic trig. But imagine if you're like doing lots and lots and lots of little tiny calculations. Like how big is the normal force? Let's like calculate a number for it. How big is this force of friction? Let's calculate a number for it. Like if you're doing like little calculations but like loads and loads and loads of them, you very quickly lose the ability to have what I would argue are important, deeper insights. Like this mass not ultimately, in the end, mattering at all. That's kind of cool. And actually it's accurate too. So just to kind of regain my focus here, if I want to find this distance in part 2, I'm just gonna write everything in blue now. Distance in part 2 is equal to, well, there's a g, an h, minus a mu, a g, a cos of theta, or sorry, alpha. And then I'd have to divide the mu and the g, because I'm after d2, I'd have to divide the mu and also the g to the other side. For the record, neither of those cancel. G is not in both terms in the numerator. Oh my goodness, this is, here my eyes are crossing because I've been at this too long, I guess. Wowie, look at this, another insight. If we had relocated this slope to the moon, but everything else was kept the same, it wouldn't have even mattered what the planetary g was. You'd go the same distance in the end anyway, which is also kind of neat. And by the way, we can make sense of that, because if we're on the moon where g is smaller, you'd have a much lower speed, because of that weaker gravity here. But you know what? Friction slowing you down would also be weaker, as you can see right here. So in the end, that's kind of cool. It doesn't matter. But what is true, and this is kind of what I was wanting to emphasize, mu definitely is not in both terms here. So canceling the g's here is valid. Canceling the mu's would be incorrect. Like if I just crossed out mu and mu, that would be a mathematical error and would not lead to the correct answer. But I think I'm on my way to the correct answer here. So H was 10.45. 10.45, that was the H. Subtract mu. And I'm going to need the angle too. I'll try to remember that. Mu 0.14, angle 27. Ooh, 0.14. So 0.14 cos of 27 degrees. It was 27 right now. Yeah, good. Cos of 27. I probably should have a pad of paper beside me that I can keep track of these things, but whatever. All of which is over mu, which is 0.14. And again, they don't cancel. They don't cancel. So grabbing my calculator, I'm going to use brackets for the numerator. Numerator, open up bracket. 10.45 subtract 0.14. Yep, typo. There we go. Multiplied by the cos of 27, close bracket, divide by 0.14. And I'm getting 73 point. My calculator says 7518. I'm just going to round this to an 8 meters. Okay, now I would say that this is, to 3 significant figures, the actually no kidding correct answer. Well, aside from my distance here, I guess, which I kept to 5 significant figures, I have a very high degree of reliability here, because I didn't really do any, unnecessary calculations with unnecessary round-offs prior to that point, or at least not many. I guess that one for sure. So anyway, if you were to do it in little tiny steps and have a little bit of extra round off accumulate, you might get an answer in the end of, I don't know, I'm just making this up, 73.7 or something like that. Like if you've been keeping 5 sig figs throughout, it shouldn't be far off from this. But in case you're curious, if you kept 5 sig figs throughout and did lots of little calculations, a slightly different manner than I showed here, and you get something that is really close to this but not exactly the same, we're pretty forgiving for that kind of thing, especially if you've been showing your work nice and clearly. So if your end answer, according to your calculations, ends up being 73.9 or 73.6 even, let's say, I'd mark it correct. Like, I wouldn't penalize that at all. Now, if you were doing sloppy things, like, you know, if you were saying, oh yeah, this is just 23, okay, like imagine a student that says 23 meters, and they kind of round off all of those digits there, and they do that several times. Like they calculate a numeric value for the force of gravity parallel, and they round it off to like 2 sig figs. That's bad. Okay, like that's going to lead to what I'm going to call the wrong answer. It's incorrect due to a very insufficient care of those precision of the digits. So anyway, 73.8 is my answer. Okay, number 7, which I think is the last. Oh no, there's number 8 as well. Yeah, okay, so 7 and 8, 2 more to go. Let's see here. Boy, do any of your other teachers do your homework for you? I don't know. I don't know if I'm doing this right. Hopefully you are not just watching these videos, sitting back and saying, oh, so that's how you do this physics. Hopefully you're not doing that. Hopefully you've made your best effort. You're checking your answers, or trying to watch these videos to gain additional insight, even if you got it correct. If you're just kicking back and watching me do your homework for you, you might think that you're getting a lot out of it. And as good as I hope that these videos are, I would argue that you're not getting all that much out of it. You really do have to sit down and do these on your own, your paper, your pen, your calculator, and importantly, I should say, a blank piece of paper that, you know, just has the question on it. Nobody walking you through it or talking you through it. Anyway, get back to work. Number 7, Jack, mass of that, competing in a diving championship. Okay, height of 3 meters above the water surface, so there's diving into water. Okay, spring with a speed of that much in the upward direction. Determine his speed when he strikes the water for part A. Okay, so let's visualize this. So there's water, and of course I'm imagining the water is level. Let's try that again. I'm imagining the water is level, but just so I'm visually remembering what's going on here, I'm kind of drawing it as if it were wavy. But let's assume there aren't actual waves that are complicating this. Okay, so Jack is right here, let's just kind of say, and I'm not even going to try to draw the diving board or, you know, anything like that. I'm just kind of focusing on what I need bare bones here. So there's an object. I don't care what happened. I don't care about the springboard. That's already done what it needs to do. So basically, at the start of this situation that I'm presented with, and I'm going to say we can treat this as our reference level. You know, let's call that the surface of the water, the reference level. I think that'd be a very good way to do it, especially since we're told it starts at a height of 3 meters. And then in part A, at least, he's going to end up H prime. Actually, let's just draw it a little closer here, because I think he just goes straight up, straight down. So he's going to go up, 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 down, 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 down. And at least as far as part A, we're only looking at like that moment that he arrives at the water surface. So don't worry about the splash or anything like that yet. I think that's coming up in part B is going to address that. So if he started with a height of 3 meters, then as far as part A takes it, he's going to end at a height of 0, which is to say the water surface. He left with a speed of 5.94, so let's say V equal to 5.94, so he's already like leapt off of the diving board, if you will. He's already jumped. And apparently he's going up, 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 down, 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 and hits the water surface. So to be clear, that's what we're thinking of right now. Okay, determine the speed with which he strikes the water. So that would be my V prime equal to question mark. Okay, remember that this is scalar. Scalar, work, energy, scalar. And no, I'm not going to do any kinematics or anything like that. Again, in the spirit of what I've been doing all along, I'll avoid kinematics where I can. So, just looking at this part of the movement, ending energy, starting energy, plus the network NC, and yeah, there's only relevant forms of energy here are kinetic and potential energy, equal to the kinetic and the potential energy, plus the work that was done along the way, network NC. There was none of that. He ends up at the height that I'm calling 0, so none of that. And I think that's it. There is, there's no network NC because the only force on the person would be the force of gravity throughout this movement. So I think that's it. And we're looking for the end speed, so let's just kind of get into this. Go back to black. 0.5 mv prime squared equal to starting kinetic energy 0.5 mv squared plus mgh. Hey, look at that. The m's totally cancel out of this equation. So if you want the v, back to black, sorry. If you want the v prime, just multiply both sides of the equation by 2. That'll clear off the 0.5. You can show this in more than one way. How about if I do it this way? Thinking as if I'm doing it like in stages here. Multiply the side by 2 does mean you have to multiply each term by 2. So if I multiply this term by 2, 0.5 times 2 is just the 1. So there's going to be just a v squared sitting here. But I do have to also multiply the other term by 2. So that's that like 0.5 kind of taken care of. I've multiplied both sides of the equation by 2. You could have also divided both sides of the equation by 0.5 and it would have been just as good. But if I want v prime and not v prime squared, I have to deal with that as well. I have to take the square root of both sides to end up with v prime. Okay, and I didn't plan this out quite very well, so how about if I take advantage of this and just kind of slide it over to give myself a little bit of extra room here. What came with it by accident? That's right here came by accident. You weren't supposed to come, I don't think. So you were, what were you? V prime, v squared, 2gh. I don't know if that was a scribble or something important. 0.5 mv prime squared, yeah, that's good, equal to 0.5 mv squared, that's good, that's mg, I don't know, hopefully I didn't just cause an error, but we'll just go ahead. Root of the following. 5.94 meters per second, 5.94, which I'll square, plus 2g starting height of 3 meters in the root. So calculator time, and no, you can't simplify this in any dramatic way. Like, don't try to square root just this first part and then separately square root this part. That's that would violate order of operations. So on my calculator, I'm opening up a bracket. No, sorry, I'm going to hit square root and then open up a bracket. 5.94, which I do have to square here on my calculator. Add 2 times 9.8 times 3, close my square root bracket, and I'm getting 9.699, etc. to 3 sig figs. I'm going to call that 9.70, I guess, would be 3 sig figs for that one. So something like that. Okay, so that's how fast he is going when he arrives at the surface of the water. Part B then kind of extends this. So here's the, let's go, by the way, that's why I was using, I guess, black ink, because there was blue in the diagram. I don't know. That's just what occurred to me. Okay, so part B, so his body has entered the water, okay? So let's think of it this way. He's just hit the surface of the water, and he's going to kind of plunge into it. I mean, he's going to end up at some depth before he comes back to the surface. And we're only considering that downward motion here, I think. So, so he ultimately arrives down here. Now, you could do this in more than one way, but how about if I stay with the water surface being a height of 0? There's no reason that I have to do it that way, but I'm going to choose to do it that way so I can explain this. In fact, let's put that over here. So how deep is he when he ends up at the bottom? Well, his ending height will be below my chosen reference level, below at a depth of 2.15 meters. So I have a negative h prime, and that is totally okay. We're below the reference level. Before stopping, okay, so v prime equal to 0. And I guess, just to be clear, from part A to part B, I've kind of reset my primes, if you will. I'm now considering this to be like the initial configuration, and this is the final configuration. I could have done that in more ways than one. I could have kept my prime here and called this a double prime, but it is what it is. It's fine. Okay, plunges 2.15 meters below the surface before stopping. Determine the average force that the water exerted on him. So as he is plunging down, there's still a force of gravity being exerted on him, but the water is exerting, I'm just going to call it an applied force. That applied force is actually going to be larger than the force of gravity, because you're moving downwards but slowing down. So the applied force is actually winning out here in bringing you to a stop. If the force of gravity was bigger than the applied force, you'd actually accelerate all the way down deeper and deeper into the water. So FYI, the applied force is big. It's bigger than the force of gravity. In fact, that's what we're looking for, right? The average force of water resistance, which I'm just calling an applied force. So the force applied, question mark. Okay, I think that's all pretty good to go. So, yeah, the usual approach. The ending energy down there, you know, when you're at your depth, is equal to starting energy. And I'm considering that the moment you hit the surface, m plus any work that was done along the way by, you know, things like water. Okay, so K prime plus U gravity prime equal to the kinetic energy, the gravitational potential energy, and the net work done along the way. What is equal to 0? Well, by the time we get to our greatest depth, we stop sinking. We started at the reference level, which, even though it's like up there, relatively speaking, it's still our reference level. It's still equal to 0. And that's it. I think everything else is non-zero. So mgh prime equal to 1/2 mv that you started with squared plus, and since we're looking for the force of the water, I'm going to save myself a small step here. That's the work done by the water, or the applied force, so F applied, distance that it applied, cosine of beta as it pertains to the applied force. Okay, this is the one thing I'm looking for, and I think I know everything else. I'm in good shape here. So let's imagine that I take this term to the left side of the equation, F applied. Let's imagine that I kept the 0.5 mv squared where it was, didn't move. I subtract mgh prime to the right side of the equation. Now, I realize I didn't write it in here, but if I had taken this whole term to the left side, it would be sitting here. But now I'm going to imagine that I've divided it down. So distance applied, cosine of beta applied. And as I proceed here, I'm kind of taking more shortcuts with my math here, which you obviously do not need to do, but I'm just trying to shave off any minute amount of time and maybe trying to give you little math tips along the way, like, you know, these little tips. Improve your algebra. If you're rusty at algebra, do continue to work at that. So the applied force is equal to 0.5. M's do not cancel, by the way. There's no M on the bottom. So we did need to know the mass, which was given as 76. Okay, so 76 kilograms. V, well, this is ultimately from part A. Now, I do like to avoid that where possible. I'm actually fortunate in that at least for me, I'm fortunate. I kept this on my calculator. I haven't used my calculator since then, so a 5-figure version of that would be 9.6997. 1, 2, 3, 4, 5. Yeah. Okay, so there's like a 5-figure version that I'll use right here for that starting speed. So 9.6997. Did you have to do that? No, you didn't. But there are certain habits that I just can't help. Okay, so minus M, 76, G, and don't lose these little details. That is a negative height. That negative is critical. You can't just like pretend it's not there. 2.15. All of which is over the distance that it applied, which we Well, actually, think about it. The distance that it applied is positive 2.15 meters. Okay, now why is it positive 2.15 meters? Because it's a distance. Distance is length of path traveled. I don't care which way you go, up, down, it doesn't. So just for the record, D applied and H prime, sorry, D applied and H prime kind of have a very, very, very close relationship here. Like they both involve the same thing, but they're subtly different. So this distance applied is legitimately positive, and this H prime, the way I've set it up at least, is legitimately negative. I don't think I've made any errors here. I sure hope not. Multiplied by the cos of the beta angle for the applied force. Well, the applied force is up, but I'll remind you that we're considering this downward movement to the bottom of, where we end up. That means that we have 180, oops, there we go, 180, oh geez, made a boo-boo there. Not 18. Okay, my computer is kind of glitching. Oh, there we go. I think we're back. 180 degrees. I'm going to enter this exactly as I see it on my calculator to get an answer. And by the way, this is the longest video yet. I think I rambled on too much. Let me know if you like the rambling on or not in a post in the classroom. Okay, 0.5. Oh, actually brackets. 0.5 times 76 times. Actually, I'll just hit answer because I think it was, oh crap, I can't remember. If I cleared it now, I won't take any chances. Yes, it is. It's there. So, brackets 0.5 times 76 times the answer that was sitting there, but I don't forget to square that. Subtract 76 multiplied by 9.8 multiplied by negative 2.15, close bracket. Whew. Okay, so that's my numerator. Divide by. Open up brackets, 2.15 times, well, ultimately negative 1, so I'll lie and say cos 180, but I actually typed in negative 1, equals. Force applied is equal to, okay, that answer does not make sense. I've got a negative number on my calculator, and this is like the size of the applied force. There's no way, no how that could be a correct answer. That means I've either screwed up a number calculation, which is totally possible, or I don't think I've made any error. Well, let's just try. Okay, let's address the simpler possibility. I'm going to clear my calculator and just try that again, hoping that I just made a typo on there. Just to clarify, the answer, like the correct answer, is guaranteed positive. When we write this work equal, like force times distance, this is the size of the force. Remember, I told you it's a scalar equation. It doesn't have a direction. So in case you're saying, no, Mr. Panis, the negative answer is because it's like up or down or what? No, sorry, that is not correct. In this context, scalar equation, the applied force is guaranteed to be positive. So something went wrong somewhere. Hopefully I just punched it in wrong. So I'm going to try that again. Bracket 0.5 times 76 times, I'll type it in this time. Maybe that's where I screwed up. 9.6997, which I don't forget to square, minus 76 times 9.8 times negative, I don't remember if I typed that in last time, maybe that's what I screwed up, negative, I bet that's what it was in fact, negative 2.15. Close bracket for the numerator, divide by, open up bracket, 2.15 multiplied by negative 1. Okay, that is for sure. Multiplied by negative 1, close bracket, cross my fingers, hit equals, and no, I get the same answer. Okay, so something's wrong. Something's very wrong. Okay, okay, so I may delete this later when I edit the video. I have no idea, but in case I choose not, maybe there's a lesson to be learned here by accident. Okay, so something's wrong, okay, and I legit don't know where it is, so let's go back and do a little diagnosis. Okay, so we have this speed, that's fine, okay, even if I made a mistake here, I mean, physically, it makes sense. It's some non-zero speed. So I'm guessing that that's totally okay. That certainly would not explain why I'm getting a negative answer right now for part B. Okay, so what the heck's going on here? Okay, let me do some detective work. And hey, this happens sometimes. I think I feel I have a good understanding of this physics. That does not make me immune from making mistakes. I absolutely still do. So let me kick back and try to figure this out. The ending energy, starting energy, work done along the way. Yep. Kinetic energy at the end, we're at the bottom where we've stopped sinking. 0 crossed out makes sense. In fact, I'll even kind of look one line down. mgh down there, we're going to have a negative height. That's good. Kinetic energy that we started with, that's that fast motion when we arrived at the surface, adding to the work that was done along the way by the applied force. Okay, I could be having my eyes crossed by now, but I think that I think I'm correct up to that point. I'm not aware of anything. Maybe when I tried to bedazzle you with my algebra, I screwed something up. So, yes. No, because I had that negative here. So let's try that one more time. So force applied, distance applied, that's negative. Okay, so by the time that negative is factored in, it'll be a negative value that I added to the other side. So, in fact, here, let's just write it in F applied, distance applied, cosine of beta, kind of as if it was there, but then I divided out later. So 0.5 mv squared, that's good. I changed this to subtract because the because I tried to subtract mgh prime over to the right side, so I think that's good. And then I divided effectively what I temporarily wrote in red here. So distance applied, cos of beta applied. And that looks good. That looks totally good. I think. I'm not seeing it yet anyway. And of course, maybe you're sitting there screaming at something that I'm like looking at and not seeing. Okay, double check my... Oh, no, that's it. Okay, okay, so 0.5 mass v squared subtract m g. By the way, g is definitely positive. Again, scalar equation, it's the size, so don't even try to think of a negative 9.8. That's not going to help. H prime negative 2.15, that's legit. Divided by the distance is 2.15. Okay, so why am I getting a negative answer? The only reason I'd be getting a negative answer is because this is definitely going to be negative according to the math. Think about it. This denominator itself is negative. Oh, wait. Maybe... Okay. I've just figured out my mistake, I think. Yeah, okay. I see it now. Hopefully you saw it before. In fact, I'm going to leave this in the video. I don't mind you seeing me fumble around. Like I said, I'm not perfect. And let's clarify where my mistake is. I'm going to leave this all in. I'm not going to cut any of that out. So here's the mistake. And again, maybe this was me getting to the point of being a bit tired and trying to do too much, trying to save time, and as a result, wasting more time than I could have saved in the first place. If you recall, I had talked about how I was trying to do like multiple steps in one. I had said, yeah, but the cos of beta is like negative, and I'm going to like take care of that and like add it to the other side. That actually was kind of like correct. Here is my mistake right here. Let me delete one more degree. Because I already incorporated the fact that beta is, or cos of beta is 180 degrees, like I already had that. I mean, I already substituted in 180 degrees, cos of which is -1, and that's how I ended up in this place in the first place. Because of my already taking that substitution into effect, this effectively doesn't belong here. I've accidentally done it again. That makes perfect sense as to why I was getting a negative answer. Because there's an extra -1 where it had no business even being in the first place. So, whoops, that doesn't belong. And what I would encourage you to do, if you're unsure of any of this, go back to this line here, and on your own, just solve for F applied. Okay, just solve for F applied. Do it any way you want to, and I think and I hope that if you do it correctly, and if I'm not making any additional mistakes, we're going to agree by the time we get here. So this does not belong, and that means that the answer I was sitting at on my calculator just was the negative of the correct answer. So if I ignore that negative, not because I'm ignoring it, but because I've diagnosed the problem and figured out that it genuinely does not belong there, it was an error on my part. So correcting for that error, I think that was the correct answer of positive now, 2,407. I'm going to round that off to just 10. So 2,410 newtons of applied force. Whew, okay, that took longer than it really should have. But hey, if you learned something from it, I'm happy. Last problem. Okay, do I dare or should I take a break? I'm going to be daring. I'll just try to regain my focus here because I probably should have had a break at some point, but this is nonstop. Like, this is one take you're listening to, and I'm not going to edit anything out, so this is legit. Number 8, get to work. Focus. Okay, Minecraft, excuse me. In fact, you know, I will take a sip of water. That's my first break all time. Oh, there we go. Okay, Minecraft, get to work. In a mine shaft 60 meters below the surface. To get to the surface, it's powered by a small 300-watt motor. The entire track is 700 meters long from bottom to top, so I'm guessing it's like an inclined plane. The minecart has a... Actually, this question I didn't read very carefully before. I'm figuring this out for the first time. The cart has a total mass of that, fully loaded. Angle of incline, so it's an inclined plane. My move's constant velocity, that's nice. Coefficient of friction between the rails and the cart. Hey, that's that rolling resistance I was talking about before, but I'll just treat it like conventional friction. How does it take, how long does it take? So we're looking for a time here. Okay, got it. So in my head, I now have kind of a visualization of approximately what's going on. I will now try to draw it. Okay, so there's the surface, okay? Like this is the ground. And I'm putting it like here because ultimately the stuff that's going on is like below the ground. So there's a point that is 60 meters below the ground. Now, how do I want to address that? I could do it in two ways. In fact, let's do it this way. Let's say that we're going to end at a height of positive 60 meters. So I'm going to declare that the ground, which is very, very frequently my reference height, I'm not going to do that. I'm going to say that wherever this little cart started, which I'm going to sketch in right away, the starting height was 0. Why not? In fact, that's often a good way to go, is the lowest point that, you know, the thing was. It's often kind of convenient to do it that way. So I don't care that that's the ground. In fact, the fact that we're in a Minecraft underground, this question could have just as easily been, if you imagine it, could have just as easily been, here's the ground, and we're going to ultimately have something that's going up a hill or something like that, or a roller coaster that's going to the top of its track. So this is fine. To get the surface powered by a small motor, okay, so the power of that motor, in fact, I don't need this huge line here, let's get rid of that. Okay, so it's going to end up here. It started here at this height. Power 300 watts. The entire track is 700 meters long. Okay, so that's the distance of the track, 700 meters. I'm assuming it's one continuous track. So in effect, if we visualize them starting here, then they have traveled up to here. This is definitely not to scale. I mean, vertically, this is 60 meters, but horizontally, along this path, it is 700 meters. Okay, so this is actually, in reality, a very gentle incline. In reality, according to the numbers. So alpha here is something that I'll probably calculate soon, maybe. Power 700 meters. Minecraft has, okay, mass was given, 193 kilograms. Oh, by the way, a random thought here. For my group of 30S Physics, when we were online earlier in the week, I asked my students, so hey, Mr. Dawson students, I'll explain this to you. I asked my students which version of the videos they prefer. Do they prefer it when I solve the problems ahead of time and then kind of make a video just kind of going over it quickly? Or do they prefer watching me actually solve the problems inside the video? And it was universal, like nobody expressed in my class the opposite opinion. Everybody told me, or everybody who voiced an opinion told me, that they prefer to watch me solve it. So maybe now you'll want to change your mind, given that I keep fumbling things up, but moving on. My mind is wandering already. Yeah, my mass is 193 kilograms. Gold ore, right. Angle of incline is constant. Yeah, it's an incline plane. It's not like curvy or anything complicated. Constant velocity. So, hey, let's just say constant velocity in the form of A equals 0. The coefficient of friction, so we'll call that mu, is 0.07. And how long does it take to reach the top? Got it. Okay, so immediately I'm thinking, I'm thinking power. Okay, I'm just kind of power is equal to force times speed, and of course speed connects distances and times. So it kind of in my head I'm forming that I'll probably do it that way. I'll probably base it on the power as force times speed equation, but that wouldn't be the only way to do it. You could do it in other ways. And I'm getting tired, so I'm going to do it just one way, so I challenge you to try it out and figure out a different way to do it and get hopefully the same answer. Okay, so I'm just going to draw this little cart at some randomly chosen point. Okay, so there is an applied force ultimately resulting from that engine that we have. So this applied force, applied power, there is going to be this is kind of like the last one that had that inclined plane. There's going to be a force of gravity parallel, but there's also going to be that force of friction, that rolling friction, and a force of gravity perpendicular, and a normal force like that. Cool. So we know that we're not accelerating, so we have perfect balance in both lines. There better be no net force amongst those. There better be no net force amongst those. So familiar situation that we've come across many times. So let's just do it this way. And again, I'm going to try to avoid just, familiar approaches here. Newton's laws and inclined planes would absolutely be a good way to go here, but I'm avoiding it on purpose. So how about if we do it this way? The power that we apply better be equal to the force applied times the speed multiplied by the cosine of beta. And I'm going to do myself the favor of just saying beta is 0 degrees. Cos of that is 1. So let's get that right out of there. For the reason of cos of 0 degrees is 1. Okay, I'll be a little bit more careful than I was last time. It's gone. It's not coming back. Okay, so how much power do we have? Well, again, because I'm trying to work my way towards time, let's think of this as force applied times speed. And yeah, rather than do too many things at once, I'll just rein it in a little bit. Power is force times speed, and you know what? No, hang on. That's not what I wanted to do. Power, because we have the power. Yeah, no, okay, let's just do it this way. Okay, my mistake. Let's just keep working within this. Power, I'm definitely tired. Power applied is equal to force applied. The force applied, we do have to connect this to, these forces. So if we're not accelerating, it's equal to these two working as a team. So it is equal to the force of gravity parallel, force, I just said I wouldn't do too many things at once, plus the force of friction, so there's the applied force, multiplied by the speed. Yes. Okay, now we know the power applied, like we have the power. So power applied is equal to the force of gravity parallel will be familiar to us, mg sine of alpha. And I think a familiar to us, I'm just going to do it, mu mg cos of alpha. Okay, so we've just got that taken care of. Okay, and so that's that, and then of course v. How are we doing? I know the power, I know the m, alpha I don't know at the moment, but that's not a problem. Mu I know, so v, yeah, so v is the one thing I don't know. And tell you what, I'll do myself a favor, since I had v written above, how about if I replace v? Since we have a constant velocity, v is equal to d over t. There's the t that I want, right there. How much time is that going to take? So let's continue on here. Power applied. In fact, let's just multiply the time over here. Okay, power applied. Okay, so it's shuffled over because I'm going to prefer it to be up there anyway right away, but let's expand this. Equal to, okay, now mg, check this out. Okay, this will be a fun one for you. I'm not even going to bother to calculate the angle of alpha because I do not need alpha. I need the sine of alpha and I need the cos of alpha. So that's what oh, actually, hang on. If I need the cos of alpha, geez, no worry about it. Yeah, okay. I was gonna do it at kind of a way of avoiding it, but I think that'll just complicate things, so I'll find alpha right now. Okay, so because I do have like ultimately the sine of alpha available to me, if you think of this right triangle, this is 60, and this, of course, the hypotenuse is given as that distance of 700, right? So a little calculation here on the side. The sine of alpha is equal to opposite over hypotenuse. That hypotenuse is the full 700 meters. So alpha is equal to the inverse sine of that. So let me just type that in. Inverse sine of 60 over 700. And it's a very gentle angle by comparison, 4.9171 degrees. Okay, now, so this is equal to, just to continue where I left off here, this is equal to mg. Actually, do I need to do anything here? Okay, I know what I'll do. Mg sine of alpha plus mu mg cos of alpha in brackets times the distance. Let's do this. Let's divide both sides by the the power of the applied. So divide the left side by power applied. It's gone, but it shows up here. Okay, so there. I just solved for time. That's a good way to go. Now I'll put all the values in. So the time is equal to, in brackets, forgive the scrolling again, M193. 193 G 9.8 sine of that value. This is the little thing I was going to do before. The sine is actually that fraction. You don't need to do the sine of it, but just for the sake of simplicity, I've done enough tricks today. 4.9171 degrees. Kind of inefficient, but it's okay. Plus mu, there's a 0.07. M again, so that's our 193, G again, 9.8. I was tempted to do factoring, but I thought I'd avoid it. Times the cosine of, I'll give myself a bit more space. This is a definite advantage of not working on actual paper. Oh, missed the bracket, but that's okay. Bracket. There you go. How lazy can you be? I'll just do it. There we go. Oh, back to pen. Okay, so I didn't finish that off yet. That was the mu mg, there we go, cosine of that same angle, 4.9171 degrees. And I think that's it for the bracketed term, multiplied by the distance. So the distance was, what, 700, I think? Yes, 700. And all of this is over the power of our little motor. 300 watts. Okay, so how much time does that take? Almost done. I hope I got it right. Brackets for the numerator. 193 times 9.8 times the sine of 4.9171 plus 0.07 times 193 times 9.8 times the cos of 4.9171, bracket to close, multiply by 700, divide by 300. And if I make a calculator mistake, like if I discover that later, maybe I'll do a text overlay just for that. But if I didn't make a mistake, I'm getting 686 seconds. So with luck, that is correct. Mr. Dawson actually sent me his answers, and I haven't looked at them yet. So I'll stop recording now, check against his answers, and if we disagree on anything, I'll figure out what went wrong and add some overlays if needed. But that's the end of this. Done.